Hello again. Thank you for joining us. So previously in this series, we introduced thin lens terminology and sign convention. We analyzed the image as it sat outside the focal point, the image of an object as the object sat outside the focal point using ray tracing and thin lens equation. We did the same when the object was inside the focal point. And we have, previous to this video, a couple of videos that we solve problems in converging lens and thin lens equations. So this video will also solve a couple problems. So please like, share, subscribe, comment. Would like to hear from you on these videos as more STEM videos will come out. So let's go ahead and begin this video. So I have an object 48 centimeters away from its image and 2 centimeters or 2 times as large. What is the power of the lens? So power of the lens, meaning we need F, right? We need F right away. So let's just see what we're given. We're given a real image. So here is the lens. A real image, if this is the object, this has to be a real image. So the object has to be outside the focal point. Here's a focal point, here's a focal point. That's the first thing. Second thing, the image is inverted, real and inverted. Okay. So whenever it says 2 times as large, the magnification has to be -2. Again, go back to the first video, the sign convention. If the image is real inverted, the magnification is going to come out negative. Again, the negative sign tells us it's inverted. Okay. So what's the power? We need F. So we don't know what DO is, what DI is, what F is. We don't know any of those. But all we know is that the magnification, which is -2, is negative DI over DO. And we know that DI plus DO equals 48. Those are the 3 things. So this is that's given, or we know. And we're looking for these. We need to find these. So let's see if from this information given, we can solve this equation, because we only have one equation to solve for F, right? And this equation has all unknowns in it. We don't know DI, we don't know DO, we don't know F. And we're trying to find F. So we need DI and DO. So let's see how we can find these two. All right. So this equation right here relates DI and DO. So let's use it. -2 is negative DI over DO. The negatives cancel out, and if I cross multiply, I get DI equals to 2DO. But that's not enough. DO could be anything, and DI is twice that. All right? We need to fix DI and DO. This is the fixer right here. No matter what I choose for DI and DO, they have to add up to 48. So that will fix them. So now, take this DI that we computed here, in other words, this value of it, and plug it into this equation. So here's this equation, DI plus DO equals 48. Take this DI and stick it here, or its value, stick it here. Its value is this. 2DO plus DO is 48. Here we have 3DO is 48. Then DO is 48 over 3, or 16 centimeters. Okay? Great. Now we know what DO is. We can easily find what DI is. DI is twice DO, or 2 times 16, or 32 centimeters. So now that we know DI and DO, we can easily plug them in here and get F. So let's do that. So 1 over F equals 1 over DI plus 1 over DO. 1 over F equals, again, multiply these two, then multiply these. DO times 1 is DO, plus DI times 1 is DI. Now to solve for F, flip both. Plug them in. So 16, well, DI is 32, times 16, 32 plus 16. Let's take it up here. F equals 32 times 16 over 48. This simplifies to 32 over 3 centimeters. To go to meters, divide by 100. So 3 times 100. And now the 32 and the 100 simplify a little bit, divide by 4. So that'll be 8 over 75 meters. That's the focal length. Okay. So again, it's roughly 11 centimeters. So the power is 1 over F, which is 1 over 8 over 75, which is, again, I have a fraction in the denominator. I flip that, so it'll be 75 over 8 diopters. And in decimal, 9.375 diopters. There is the power of the lens. And now for verification using ray tracing. Here's the blue ray parallel as it exits the lens, goes through the focal length. The green ray through the center, exits unbent. The orange one goes through the focal point, comes out parallel. They meet here, 32 centimeters, twice the size of the object. Right? The focal length is roughly at 11 centimeters. Right? Each of these is 4. Well, and this is it for this problem. Let's move on to the next one. So question is, how far away from a 16 centimeter focal length converging lens? So right away, focal length is 16 centimeters. Should an object be placed such that its image has the same height? Okay. So the image will have to be real, but we want them to be the same height. And have the virtual image here the same height as the object. Okay. So what we need to do, we need to find out the image that has the same height. I mean, we need to find the magnification for this situation. The magnification is going to be negative 1. Okay. And if we're not sure about this, so again, let's just take a number. If HO is 2 centimeters, HI has to be negative 2 centimeters. At the same height, but one is pointing up, one is pointing down. So the magnification is HI over HO, negative 2 centimeters over 2 centimeters, or just negative 1. So again, magnification of 1, okay, means the object is, they're the same height, the absolute value of the magnification is 1, but we have to take into account the sign reflecting the orientation of the object and the image. The object points up, it's positive. The image points down, is negative. So now that we know the magnification, we can relate the distance, the DI and the DO, okay? Because again, I know the focal length, but I do not know DO or DI. So I still have a problem with one equation, two unknowns. I need to find a way to relate these two unknowns. And this is how we're going to relate them. Magnification is also defined as negative DI over DO. But it's negative 1. That means 1 equals DI over DO. The minus sign cancels out. Or the distance to the image is the same as the distance to the object. That is an important finding. Okay, so now we can use the thin lens equation. 1 over DI plus 1 over DO equals 1 over F. So DI is DO, so 1 over DO plus 1 over DO equals 1 over F. Here I get a common denominator of DO times DO, or DO squared. And here, again, cross this. DO plus DO. There's 1 over F. Let's go up here. So flip now. F equals DO squared over DO plus DO is 2DO. So what do I have here? DO squared, DO, one of them cancels out. This cancels one of these out. So now I can cross multiply and find that DO is 2F, or 2 times 16, or 32 centimeters. So the image to the object is 32 centimeters. The image to the distance to the object is 32 centimeters. The distance to the image is also 32 centimeters. And here is we did not need this page. Magnification was not asked for. So here it is again. The blue ray parallel from the tip goes through the focal length. The green one through the center continues. The other one, the orange one, through the focal point, hits the lens, comes out parallel. They all meet here. Image is inverted and real and the same size as the object. Right? And next, this is it for this series. But next, we're hoping to do the diverging lens series, similar to this, and then do other STEM topics like math, algebra, calculus, some engineering, some robotics. So again, please like, subscribe, and follow us so you can get all these notifications when we release new content. Again, thank you for your time, and we'll see you in the next video.